So we're about to move into programming structures. This is the exercise from session 7 where we talked about factors, and the exercise is based on Pascal's triangle that you see here in front of you on Wikipedia. And Pascal's triangle is, let's read what it says. In mathematics, Pascal's triangle is a triangular array of binomial coefficients. It's named after the French mathematician Blaise Pascal. One of the oddities, characteristics of Pascal's triangle is that you could obtain the entries, the cells for any one row n by adding up the rows, by adding up the elements that are in the preceding row n minus 1. For example, you can see here when we go down to depth 4, there are 4 entries, 4 cells, and we have ones along both of the sides, and then this cell is the sum of these two, this cell is the sum of these two, and so forth. Let's shift now and take a look at what the assignment said. Note this little animated GIF down here. It is demonstrating what I just explained. The numbers are adding up from the corresponding adjoining cells in the row above it and thus forming the values in the row beneath it. Here is the original assignment, and again, here's Pascal's triangle, and it can be represented as a list where item n is row n of the triangle. So this is the node, the top. This is the n equals the first row, n equals 1 if you consider the top one to be 0. This is n equals to 2, n equals to 3. Otherwise, this would be 1, 2, 3, and 4. The assignment was this: write a function that, given Pascal's triangle to depth n, let's assume that this is 1, returns Pascal's triangle to depth n plus 1. Verify, for example, that the 11th row gives the binomial coefficient of 10 indexed by 1 for I equals 0, 1, all the way up to 10. Well, so how would we do that? Well, let's take a look at the script 1 solution in RStudio. Here is one solution, and actually this solution is comprised of 2 functions. We have Pascal's increment, which adds the rows at whatever the depth is, and then we have a second function which actually builds the triangle called Pascal. It builds the triangle by calling increment, which actually adds the rows at whatever the depth is over and over again. So let's start up here. Let's clear everything out here. So we'll clear that out, and we'll clear out the console. So how does increment work? Well, increment works by accepting as an argument a list that has this form. And so the PT is assumed to be a list with a length of at least 1. So you can pass in PT a list, which is the the current level of Pascal's triangle. And the first thing that it does counts the elements in the current list that's passed in. We have a count of the elements, and then if there's only 1, it knows it's the very top. So if it's 1, it just simply returns the second level, which is a list with 1 at the top and then 1, 1, which would be the second level. Or actually, this is level 0. We're assuming the top level is 0, so the second row would actually be level 1, I guess. So then it stores the current element, the current vector that is the element in the component. It puts that in PTN. It counts how many elements there are in that current component, and then it adds the row or the component beneath it in the triangle, which just simply is conceptually the next element for the component that follows the current one in the list. So it's pretty easy to see if you look at this. So it's adding all the in-between numbers between 1, which is on the outside. If we go back and look at Pascal, you can see it here in the assignment. Got 1s on the outside, and then we have summations on the inside. Well, that's exactly what we're doing here. It's adding the numbers on the inside for the row beneath it, and that's what it returns. So let's Get that? So we grab that, and then the Pascal function actually builds the triangle by successively calling increment, which builds the rows, as long as I is less than n. So as long as this is true, it keeps building it. It stops being true when it's called it to whatever level n is. So we need to load that in as well, and that's what gets returned ultimately, is the entire triangle. So let's, if we load this up too, this is one version. Okay, so note that when we call Pascal, Pascal calls the increment over and over again and builds the subsequent rows beneath it. So let's do it to a depth of 4. If we call Pascal to a depth of 4, you can see there's the top one, then 1, 1, the second one, then 1, 2, 1, then 1, 3, 3, 1. So that seems to work okay. Now, note that we can do this instead of doing it in the fashion that we did, where we have one function that will add the row beneath it and a second function that just simply builds the triangle by calling the row adder over and over again. We could do it recursively like this, where this calls the same function. So we have Pascal recursive. We're just simply calling the same function over and over and over again to add the rows beneath it. So this accomplishes the same thing. It's a bit more complex and a bit more hard to understand. From a programming point of view, you're really better off making the individual functions cohesive, loosely coupled and cohesive. That is, each function should do one thing and one thing only. So it's not a bad idea to have a function that adds the rows and then a second function that will keep adding rows to whatever depth is required. But it isn't difficult, on the other hand, to simply add that all into one function, one that adds the rows, and then it just keeps calling itself until n is at the depth, the proper depth, until you've added all the rows up to n. So if let's load that up. Let's call it, let's call it to 4 so we can see everything. This is the original one, actually. So that's the original non-recursive function. And let's modify this quickly. We'll say Pascal recursive. And this is calling the recursive function just above. Does the same thing. So let's try it again. The exercise actually said to 11, the binomial, these are binomial coefficients in Pascal. That's one of the characteristics. There are other characteristics, but it creates binomial coefficients so that for the 11th row has the binomial coefficients of 10 indexed I. So that's true. So if we do it to 11, there are the binomial coefficients for 10 because the top is 0, and Pascal recursive, take a look at that. Pascal recursive returns the exact same set. So there you go. So let's get into programming structures. No discussion of programming structures would be complete without at least a cursory coverage of loops and scoping rules, but we're not going to belabor this because we've talked about it before. So we'll do this quickly and then we'll get into some more complex examples. Loops are one way that you can perform repetitive tasks. So let's look at one. The one loop is the for loop. The for loop will loop over vector sets. The vector can be any mode. So let's look at a quick example. Here's the syntax where you have for, and then you have the vector that you're passing in is x, but it will repeat one iteration of whatever is in the body for n. N will take on the values that are in vector x. So let's take a look at an example of this. So here's x. It's just this vector. It's 5, 12, and 13, and we're gonna print it. We're gonna make it come out on the screen, but we're gonna square each value. Note it's vectorized. That's important to note. So we'll get 5 squared, 12 squared, 13 squared. So that's what we see. Now you can do the same thing. These are control statements. You're controlling what line the interpreter is on, and therefore what line it is actually executing. While and repeat do the same thing, but it's just a little different. The distinction with for, the for loop you should use when you know exactly how many iterations you need. That's really the defining characteristic, whereas while and repeat should be used when you don't know exactly how many iterations you need. You use while and repeat. It iterates as long as some condition is still true. You test a condition to see if it's true, and if it is, you loop another time. Here it's hardwired. You're saying I'm going to loop this many times, and so that's why you use for when you know exactly how many loops you need. So let's take a look. Here we just set I equal to 1, and while tests this condition, and as long as this condition is true, it will keep performing this over and over again. So if I is 1, let's do this, I is 1, and we say while I is less than or equal to 10, I want you to make I whatever I plus 4 is. So we do that. And note what comes out when we say, okay, when we're done with that, what is I? The value of I is 13. So that means it kicked out of this loop. This loop captured it, if you will, and kept executing until I was 9. That was the last time it was in the loop. Well, what happened? We come in here, I is 1. Is I less than or equal to 10? Yes, it is. So I becomes 1 plus 4, or 5, it comes back over here. 5 is 5 less than or equal to 10? Yes, it is. So I becomes then 5 plus 4, 9, comes back in here. It says is 9 less than or equal to 10? It is. So I over here becomes 9 plus 4, 13. So I is 13 at this point. When it tests the condition again, it says, is 13 less than or equal to 10? No, it isn't. So it exits the loop. That's why we get a value of 13 over here. You can do the same thing a number of ways. Here, this is kind of really bad programming. This is the same thing as putting a condition in here that's always true. If we just said while true, that means every time it's true, every time it checks it, it's true. So it'll loop infinitely, but you can trick it. You can fix it by putting break. Break causes it to exit when this condition is true. Okay, so this is a way to do it, and it's not very good programming. So we do the same thing. We make I 1, and while it's true, then we add 4 to it. And in this case, when I increments gets above 10, we kick out. Well, it does that when I becomes 13 in the same place it did last time. So here we get the same answer with another way to do it that demonstrates break predominantly. I don't recommend doing that. Here's another thing you can do. Repeat. Repeat doesn't have a condition. There's no Boolean exit condition with repeat like there is with while. This is a Boolean exit condition, which is always true. Up here in this first one, it's not always true. This is Boolean as well. If I do this, look, it returns a true or false. It's not returning a number. It's true or false. So, but unlike while, repeat has no Boolean exit. So again, we can trick it the same way with break. So let's do that. So we make I 1, then go through this repeat, and again we get the same answer. You can also use next. Next works in a way that's similar to break. It instructs when next is encountered in a line, it instructs the interpreter to exit the current iteration of the loop. It goes down to the next place where there is control. It skips whatever lines that are included in this iteration and just proceeds directly to the next one. But it can really be confusing. For example, here's an example. It really doesn't matter what all this does, but we note when we come down to here, when it encounters, here's an if statement with a next. And when it encounters this, what happens is, so if this is true, it sees this executes because the condition is true. And what this does, it causes it to skip all the way out of this iteration. So it's going to skip this line, it's going to skip this line, and it's going to skip this line. It skips everything in the body of the current iteration, which is governed by the for. So what happens if this is true, it goes back up to here. It doesn't start here. It goes back up to the top of the for. This does the exact same thing. So in this case, if this is true, if none may be chosen, is again same thing. It goes up here. Next is not a good idea. You can replace nexts with nested ifs, which can be easier to understand if you have a small amount of levels. So we can take a look at this.